this is the new topic, basis, and the definition is, let V be the vector space over a field F. A non-empty set V1, V2, V3 up to Vn of V is said to be a basis for V if first condition, V1, V2, V3 up to Vn are linearly independent and V is generated by these vectors. Now V1, V2, V3 up to Vn, these all vectors are belonging to the vector space V, right? And these vectors, this set of these vectors is said to be the basis for V if these vectors are linearly independent and V is generated by these vectors, which means these vectors are the generators of vector space V, right? Recall that if every element of V is a linear combination of these vectors, then we say that V is generated by V1, V2, V3, Vn. Another definition for this generating set of V. Suppose this is your vector space V and V1, V2, V3, V4, V5. These all vectors are belonging to this vector space. And there is one more vector in purple color, small v. This is also belonging to this vector space. And the definition says that if every element of V is a linear combination of these vectors, V1 up to V5. Here I have taken 5 vectors. So if V is equal to alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 plus alpha 4 V4 plus alpha 5 V5, where this alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, these are the scalars, right? If every element of V is a linear combinations of all these 5 vectors, then we say that these 5 vectors are the generators of the vector space V. And together this set is known as the generating set of V, right? Okay. Let's start with the assignment 1. The example is, prove that 1001 is a basis for two-dimensional space in R, and I'm calling this as R2, right? So now the proof is, I have to show that these two vectors, the set is a basis for R2, two-dimensional space, right, in R. Now to show these two are the bases, I have to show first thing that these are linearly independent, and second, V is generated by V1 and V2. Let's say this is V1 and this is V2. And what is our capital V? This is our V, right? 2D vector space, right? Okay, now first condition, let's show that these two vectors are linearly independent. So for that, let's take the linear combinations, and I'm taking my scalars to be alpha and beta. So let's take the linear combination first. That alpha, sorry, I must change the color of the pen. Thank you. Let alpha 1, 0 plus beta 0, 1. This is equal to 0, 0. Fine, I have written these vectors to be the linear combinations with scalars alpha and beta. Now to show that for this identity, all the scalars are equal to 0, then only we can say that 1, 0 and 0, 1 are linearly independent. So this implies if I multiply, I will get alpha, beta. This is equal to 0, 0. Is it fine? Alright, let me write one more step. This is nothing but alpha, 0 plus this is 0, beta. Is it fine? Just multiply them and then adding, we get alpha, beta. Now is it right? Okay. From here, what I get this implies alpha is nothing but 0 and beta is also comes out to be 0. So all the scalars are 0, hence the vectors 1, 0 and 0, 1 are linearly independent. First condition for basis is proved. Now the second condition, that these are the generators of R2. For that, let me take one element from R2. Likewise, we have taken the element from this vector space, we have taken V. So every time we need to take an element from the given vector space. Now here our vector space is R2, so I have to choose one element from R2, and let's say that element is x comma y, because it is a two-dimension space, so I must have an element like this, x comma y. And x comma y, this is, I have to write this vector to be equal to linear combinations of 0, 1 and 1, 0, right? If I able to write this vector as a linear combinations of the given vectors, then I say that those vectors are generated by this vector space R2. So I'm writing xy to be equal to, can I write this as x comma 0 plus 0 comma y? If you add these two, you will get back xy. So xy can be written like this. Alright, take x common from here, I get 1 comma 0, plus take y common from here, I get 0 comma 1. And these are nothing but my given vectors, which means I have now written that this vector is a linear combination of 1, 0 and 0, 1. So therefore, xy is a linear combination of these vectors, right? Because xy is arbitrary, which means every element of R2 is a linear combination of these vectors. This is what is the definition for the generating set. The set that generates the vector space is that every element from that vector space should be the linear combinations of these vectors. So therefore 1, 0, 0, 1 is a basis for R2. So both the conditions are proved. One is these are linearly independent. Second, these are the generators of R2. Right? So we have proved both the condition. Hence these two vectors forms the basis for R2. Alright, easy? Okay, let's move on to the next example. Find the basis for R3. Now, it's a three-dimension space in R. So for that, okay, in this example, I'm proving the second result first, that the basis for R3 I have to find. So I have to take the linear combinations, right? I have to prove that those are generating set. Whatever vectors I will get to have, that are the generators of vector space R3, right? So for that I need to take one element from R3, and if I write that element to be the linear combinations of the elements of again R3, and I prove that if every element of R3 is a linear combinations of some vectors of R3, then I can say that my second condition is proved, right, for basis. Okay, let's take one element from R3, which is, let's say, x, y, z. Fine. Alright, now how can I write x, y, z? Just likewise in the previous example, right? This as x comma 0, 0 plus 0 comma y comma 0 plus 0 comma 0 comma z. If you add all these, you will get back your xyz. So xyz can be written as this? Yes. Now taking x common and then y and then z. So now I get that this vector is a linear combinations of 1, 0, 0, 0, 1, 0 and 0, 0, 1. And all these vectors are belonging to R3, isn't it? Yes. So now xyz is a linear combinations of these vectors, but xyz was arbitrary, which means we have proved that every element of R3 is a linear combinations of 1 0 0 0 1 0 0 0 1, right? So second condition is proved. Now about the first condition, that these vectors are linearly dependent, right? Okay, so let me take first the linear combinations with my scalars alpha, beta, gamma. Okay, so I'm taking this as alpha 1, 0, 0. Why I have proved the second condition first? Because I need these vectors. How do I know which vectors should be linearly independent? I have to find those vectors first. That is why I have proved the second condition first for the basis, right? And now I got these three vectors. Now I will prove that these are linearly independent. Okay. So, okay, alpha times 1, 0, 0, beta times 0, 1, 0 plus gamma 0, 0, 1. So, I have written the linear combinations of these vectors equal to 0, 0, 0. This is our identity. So, which means I get, just multiply this, alpha 0, 0 plus 0, beta 0 plus 0, 0, gamma. Finally, I will get alpha after adding alpha, beta, gamma to be equal to 0, 0, 0. This implies alpha is equal to 0, beta is equal to 0 and gamma is equal to 0, which means all the scalars are 0, which means all these vectors are linearly independent because their scalars are all 0. So we got the result that this 1 0 0 0 1 0 0 0 1 are the generators of R3 vector space, and also these are linearly independent, which means these forms the basis for R3, right? Okay, let's move on to the third example. Find a basis for Rn. Just now we have find the basis for R3. Now I have to find the basis for n-dimensional space in R. Very easy. We have to just repeat the steps but in n dimension. So again, because I need my vectors to prove them to be linearly independent to form the basis, right? So I will try to prove the second condition first. From that I will get the vectors. So the second condition is that we have to find out the vectors which are the generators for Rn. Let's find out. For that I need the element from Rn. So let me write, okay, this is x1, x2, x3 up to xn. Let this element belongs to Rn. How can I write this element is equal to? This is actually a vector, right? How can I write like this equal to? Yes, simple. Take x1 and rest of them take 0, 0, 0 up to 0. And then for x2, give the values rest to be 0. And then for x3, take all the values rest to be 0 up to so on. For xn, take all the values 0 but last one as xn. If you add all these, you will get back x1, x2, x3, xn, right? Now take common x1, this is 1, 0, 0, 0, so on. Then x2, 0, 1, 0, 0, so on. Then x3, 0, 0, 1, and so on. This is xn, 0, 0, 0, up to 1. Let me call this first one as E1, and sorry, let me call this first one as epsilon 1 and this to be as epsilon 2, this to be as epsilon 3, and this is to be as epsilon n. So x1, x2, x3, xn, this is a linear combination of epsilon 1, epsilon 2, epsilon 3 up to epsilon n, right? But this was arbitrary, thus Rn is generated by epsilon 1, epsilon 2, epsilon 3 up to epsilon n. Now I got all my epsilons, which means I got all the vectors now. In the second condition, I just need to prove that all these are linearly independent and then my job is done. So now let's take the linear combinations of these. Let me take as alpha 1 with epsilon 1, then alpha 2 with epsilon 2, then alpha 3 with epsilon 3, up to so on, alpha n epsilon n. So this is equal to 0. Then put the value, this is 1 0 0 0 plus alpha 2 0 1 0 up to 0. Then alpha 3, this is 0 0 1 0 0, and then go on. Alpha n, this is 0 0 0 0 1, and this is 0 0 0 up to 0, which implies if you multiply alpha 1, alpha 2, so on, and adding all these, you will get alpha 1, alpha 2, alpha 3 up to alpha n is equal to 0 0 0 so on. This implies alpha 1 is equal to alpha 2 is equal to alpha 3. All are these equal to 0. So all the scalars are 0 now, which means epsilon 1, epsilon 2, epsilon 3 up to epsilon n are linearly independent and Rn is generated by these. Therefore, this complete set is a basis for Rn. Right? Okay. Now there is a remark for you. Now epsilon 1, epsilon 2, epsilon 3, epsilon n, this generating set is called the standard basis for Rn. And in particular, if I take 1 0 0 1, this is the standard basis for R2, 2 dimension, and 1 0 0 0 1 0 1 0 0, this is a standard basis for R3, 3 dimension space. So please remember this. Whenever you're having the 2 dimension space, take 1 0 0 1. For 3 dimension space, take 1 0 0, then 0 1 0, then 0 0 1. Right? Then 0 0 1. I'm very sorry. It should be 0 0 1. So this is the standard basis for R3. So please keep this in mind. Take this as your remark. And we meet in the next video and we solve some more examples on this. Thank you so much.